Okay, so we discussed random variables before, and we worked out, for some simple cases, we worked out the expectation and the variance of them. Okay, this time in this session we'll look at uniform and Bernoulli random variables. There are infinitely many random variables, so we can't possibly discuss all of them, and not all of them can have names, but there are some which are, they come up so often in applications that they're worth taking a look at. Okay, so we're going to start with the discrete uniform. So there's a discrete uniform random variable, and there's a continuous uniform random variable. We'll talk about the discrete one first. And the idea here is that by uniform in the discrete case, what we mean is that there are a certain number of values for x that x can take. And the probability of x taking any one of those values, small x, is exactly the same. Okay? So that's why we call it uniform. By that we mean that the probabilities are the same. So let's take an example. If we toss a coin, and the discrete random variable has 1 for an h and 0 for a t, and it takes no other values. It only takes the values 0 and 1. Well, what's the probability that x equals 1? What's the probability that you get an h? What's the probability of getting an h for a, okay, well, let's assume that the coin is fair. What's the probability of getting an h? 1/2. Okay, what's the probability that x takes the value 0? That's the probability of getting a t. For a fair coin, the probability of t is 1/2. Okay, so note that there are, in this case, 2 allowed values, and their probabilities are exactly the same. So we say it's a discrete uniform. This x is an example of a discrete uniform random variable. Okay? The probabilities for the various, that x takes its various allowed values are exactly the same. Hence the word uniform. Okay? All right, and then we might write the PMF like this. Okay? The probability that x takes the value small x, for small x being the allowed values of 0 and 1, is the same, 1/2, and it's 0 otherwise. Okay, so again, this is an example of a discrete uniform random variable. Okay. So here's another one. We're going to roll a fair die, standard 6-sided die. X takes the value of the roll. So it's a fair die, so it can take values 1, 2, 3, 4, 5, 6, all with the same probability, 1/6, and 0 otherwise. So once again, we say that this is an example of a discrete uniform random variable because the probability that x takes any one of the allowed values is exactly the same. Okay, so again, and 0 otherwise. So uniform, because that 1/6 is the same for all the allowed values of x. Okay. So, all the possible values of x have the same probability, so x is a discrete uniform random variable. Okay? All right, now roll 2 die, x is the sum of the results of the roll. Okay? So what values can x take? 2 through 12, and the integers 2 through 12. Okay? Why is x not a discrete uniform random variable? Right, so the probability of a 2 is different and the probability of a 7 is different, right? Right. 7s are more like, rolling a 7 is more likely, has a higher probability than rolling a 2 or a 12. Okay, so, is it different? Okay, so if we want to write this in a general way, we say, what's a discrete uniform random variable? Okay, so we say, well, x can take these values, x1, x2, up to xn. Okay? And all the values then, the probability of each one of the values given by this PMF is 1 over n, otherwise it's 0. So we saw a couple of examples of a discrete uniform random variable that fits this form. And we saw an example of something which is not a discrete uniform random variable. Okay. Any questions about this? No? Okay. So in our coin flip example, right, the PMF for x is the same for the 2 allowed values of f. There are 2 allowed values, so the PMF value would be 1 over 2 for those, and 0 for anything else. Okay? For the rolling the die example, what do you have? You have 1 over 6 for x is the 6 allowed values, right? So okay, you'd have 1 over 6, and you would have n equals 6. For the die example, for the coin flip example, you have 1 over 2, and you have 2 allowed values, x1, x2 for your x, right? So anything which fits this format, any discrete random variable which has a PMF that looks like this is called a discrete random variable. Okay, so the expectation of x is the sum over all the allowed values of x, we're calling those xi, times the probability that x takes the value xi, which is the PMF evaluated at xi. Okay, so now what's that probability? We said that that probability was 1 over n, right? So so it's the summation over the xi's times 1 over n. 1 over n is a constant, right? They were n, right? Remember, n is the number of possible values that x can take, all with equal probability. So you pull out the 1 over n. And then, and so what is this? This is the mean of, or the average of, all the allowed values. So the expectation for a discrete uniform random variable where all of the outcomes have the same probability is the average of the outcomes. Is that okay? Right? Okay, so as an example, the expectation for the coin flipping case, it can take the value 0 with 1/2 plus a value of 1 times the probability of 1 is 1/2 is 1/2. Or if we remember this formula, we'd say, okay, 0 plus 1 over 2. All right? Okay, what about for the rolling the fair die example? What do we have? Right. So the sum over I goes from 1 to 6. That's this, and then 1 over 6. Okay, whatever that turns out to be. Okay. What about the variance for the discrete uniform random variable? So for any random variable, I would want to know at a minimum what its expectation is and what its variance is. Okay? Now, there are other things that we can know which involve higher powers of the random variable, but these are the two minimum that I want to know for any random variable. Okay, so what do we have? The variance of a discrete uniform random variable, or you can write it both these ways, is the expectation of x squared minus the expectation squared. Okay? Now, so what do you have over here? You have then this part, the expectation of x squared, is right? So it's expectation, sorry, it's the expectation of x squared. So that's the formula for the expectation of x squared, right? Now, it's a uniform random variable with n possible outcomes. So what's this probability? 1 over n. So this is, we can pull the 1 over n outside, and we have the summation of xi squared. So this is the average of the squares of the values, right? And then you're supposed to subtract off the expectation squared. Okay, but what was the expectation? It was the average of the xi's, right? So this is equal to 1 over n times the sum of the squares minus the sum of the values. Sorry. I'm messing this up. Let me not simplify. 1 over n times the summation of the squares minus the summation of the xi squares times 1 over n squared. Okay. All right, so for the discrete uniform random variable, figuring out these things is maybe not so difficult, right? Yeah.
There is something we were talking about at the beginning, that if x is the sum of two rows of a die, that is not a uniform random variable, but it could be a random variable.
Yeah, so rolling two dice, gives, and saying that x is the value of the sum of the two rolls, that is not uniform because the probability of a 2, for example, is not the same as the probability of a 7. But it's a random variable. So it's just not a uniform random variable. Okay. All right, so that was the discrete uniform random variable. Let's talk about the continuous uniform random variable. Okay? So this is the form for a continuous random variable, which is uniform. That means that it's defined on it takes values on an interval from A to B. That's what makes it continuous, right? And now we don't talk about a PMF, we talk about a PDF, a probability density function. Before it was the probabilities which were all the same. Here it's the probability densities which are all the same. Okay? So on the interval from A to B, the probability densities are the same. Now, what should they be? Well, if you integrate the probability densities, right? If you integrate the PDF, you're supposed to get 1. So outside of the allowed values of x, which run between a and b, you get 0. So now you need to be able to integrate the PDF from a to b, and that should be equal to 1. Well, what can you integrate? What constant can you integrate on the interval from a to b and get 1? Well, that constant would be 1 over b minus a. Okay? Okay, so if I looked at the graph of this, here's A, here's B, I suppose I shouldn't have these actually. Okay. So all the way from minus infinity to A, it's 0. Then it jumps up to a constant value. And then at B, it drops it back down to 0. So when I integrate the PDF, all I need to do is integrate from A to B. And it's supposed to be uniform, which means that the probability density should be the constant. And then the constant that you need, so the integration will come out to 1, is 1 over b minus a. Okay? So a random variable, okay, all right, so I need to integrate from minus infinity to infinity. I need to integrate the PDF, and I have to get 1. If I integrate the probability density over all reals, I'm supposed to get a probability of 1. Okay? Now, I'm saying that it's 0 up to A, and it's 0 past B, so I only need to integrate from A to B. Right? And we're saying it's uniform, which means that the probability densities at the allowed values are the same. So this has to be a constant. Right? Well, what's this? This is equal, if I integrate over x, this is k times b minus a, and that's supposed to integrate to 1. So that constant must be equal to 1 over b minus a. Is that okay? All right. So any continuous random variable whose PDF is defined in this way, with this form, it's 0 outside of the interval, outside of some interval, and on that interval, it's 1 over the PDF takes the constant value 1 over the length of the interval. That random variable is called a continuous uniform random variable. Is that okay? Okay. Well, all right, so let's find its expectation. How do you find the expectation of a continuous random variable? You integrate from minus infinity plus infinity x times the PDF at x dx. Right, by the definition of the expectation. Okay, in this case, the PDF has the form 1 over b minus a on the allowed interval. I don't have to, we had this discussion, I don't have to integrate outside of it where it's outside the interval where the PDF is 0. So I integrate where we have a non-zero value for the PDF from a to b. The PDF on that interval takes the value 1 over b minus a times x dx. Okay? And if I do that integration, I get a plus b over 2. Oh, Okay? So it's uniform. If it's uniform on an interval from A to B, the expected value is the midpoint of the interval. Okay? Any questions about that? All right. Well, let's calculate the variance now. Okay, the variance is the expectation of x squared minus the expectation squared. Okay, so that's the integral from minus infinity to infinity, x squared times the PDF evaluated at x dx, minus the expectation squared, which was a plus b over 2 squared. We just found that. And the expectation of x squared, by definition, is this thing here. Okay? Now, I don't bother to evaluate the integral outside of the integral, because that's just going to give me 0. You know, I could break this up into 3 parts. I could say the integral from minus infinity to infinity is the integral from minus infinity to a, plus the integral from a to b, plus the integral from b to infinity. Right? You can break up integrals that way. But the integral from minus infinity to a is going to be 0 because of the form of the PDF. The integral from b to infinity is going to be 0 because of the form of the PDF. So I'm only really left with having to do this integral, the integral from a to b, x squared. Now what's the PDF value? It's 1 over b minus a on that interval from a to b. Okay, so I can pull the 1 over b minus a outside. I can integrate x squared as 1/3 x cubed, evaluated at b and at a. So what I get when I do that integral is this. I square this to get this, and then this can be rearranged in this form. Another random variable that we are going to use a lot, and it comes up in a lot of important applications, is the binomial random variable. Okay? And then later on we'll have the multinomial random variable. We start with the binomial first. Okay? So what we're going to do, I'm going to build up the theory by starting with a specific example and then moving towards the more general form. And as we're going along the way, the PMF for this is just going to fall out of our considerations. Okay, so let's say we toss a coin 7 times and we record the number of H's. Okay, let's make the coin fair for now. So getting an H has a value p equals 1/2. The probability of an H has p equals 1/2. The probability of not getting an H is the probability of the complement, Q, let's call that. There's 1 minus p, which is also 1/2 for a fair coin. Okay? All right. What's the probability of getting no H's? You're going to toss a coin 7 times. The coin tosses are independent of each other, so you can multiply probabilities, right? So what are you going to get? Right. You're going to get q to the 7, which is, in this case, it's 1/2 to the 7. Later on, we're going to allow p and q to vary. But for now, it's q to the 7, which is the same as 1/2 to the 7. That's the probability of getting no H's. Okay? What's the probability of getting exactly this sequence? Remember, coin tosses are independent. So the probabilities are multiplied. right? All right, so this is going to be, the probability of an H is P to the 1, right? And then you get 6 T's. The probability of a T is Q. So because they're independent, right? So you're going to get P to the 1. Q to the 6 is the probability. Is that okay? All right, which is the same. In this case, P and Q are the same. So this is still going to give you 1/2 to the 7. Okay? Okay, but I'm going to write that as P to the 1, Q to the 6 because later on I'm going to be, I want you to see this form. Later on I'm going to allow P and Q to vary. Okay? What's the probability of exactly this sequence? Yeah. Okay? So this one would be, again, coin tosses are independent. So the probabilities can be multiplied, right? Probability of A and B, A intersection B is probability of A times probability of B when A and B are independent. So this is Q, probability of not getting an H is Q, and that's been done 1, 2, 3, 4 times. And then there's a probability of an H. And then there's 2 T's. Okay. PQ to the 6. P to the 1, Q to the 6. Is that okay? Now let me ask you a different question. How many sequences are there such that one element of the sequences of H and T's, 2 distinct symbols, how many such sequences are there such that one of the elements is an H and 6 of the symbols are T's? How many sequences?
7.
Right, there's 7. So one way of thinking about that is there are 7 places to put in an H, right? And the rest are all automatically T's. So there are 7 such sequences. The other way to look at it is that there are 7 places you choose 1 for your H and the remainders are T's. So it's 7 choose 1. The other way of looking at it is that there are 6 places to choose for your H's, so, right? So there are 7 choose 1 sequences in which there is 1 H and 6 T's. Okay. 7 choose 6 would also give you the same thing, right? Right? Think, yeah. 7 choose 6 is equal to what? 7 factorial over 6 factorial, 1 factorial, which is in fact the same as 7 choose 1. Okay? Okay, right. Well, the choose concept in this question, when we say how many ways are there to how many ways are there to, one way of looking at it is if I've got these 7 slots, I have to choose one of them for the H, right? And then the rest can go anywhere. So 7 choose 1. Because then the t's are automatic, right? Okay. Okay, so now let me ask you. The probability of getting 1h and 6 t's, and it doesn't matter where that h goes. What's the probability of that event? Well, we can think of that event as being broken up into different events, right? As the union of different events, right? It's the probability of getting that h in the first slot plus the probability of getting the h in the second slot, and so on and so forth, minus some intersections, but minus plus some intersections, but the intersections of those events are empty. It can't be in the first slot and in the third slot, right? So we have to add up all the probabilities, right? So there were 7 choose 1 ways of doing it, and the probability of each one was what? P to the 1, Q to the 6, right? Each one of those slots, each one of those sequences, which have 1h and 6 t's, had the same probability. P to the 1, Q to the 6. And how many such sequences were there? 7 choose 1. So what's the probability of having 1h without any restriction as to which part of the sequence which slot in the sequence it's in?
7 times.
Right. The sum of all of those, there are 7 choose 1 ways of doing it. Okay? So, each sequence that we're specifying here has a probability of P to the 1, Q to the 6. And there were 7 choose 1 such sequences. So the total probability of getting 1h and 6 t's, no matter where that h lies in the sequence, is the sum of all of those. So 7 choose 1, P to the 1, Q to the 6. All right. Is that all right? Okay.
We also noticed the time probability of one certain sequence where h is greater than 1. And we multiply the probability of that with 7. So we're not seeing
Yes. 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 I mean, this is basically what we're saying, is that each one of those sequences has a probability P to the 1, Q to the 6. And how many of them were there? Well, there were 7 of them. So add them all up, add up all the probabilities, and that's the probability that we're looking for. Okay. What do you think about this? What's the probability of getting 2 h's in a row followed by 5 t's? What's the probability of that? Okay, once again, your coin flips are independent, right? So what are the probabilities? So it would be P squared Q to the 5 of this sequence. Now, what about all the other sequences which have 2 h's and 5 t's? They're the same, right? They're the same. So right? So this has a probability P times Q times Q times Q times Q times P, once again, P squared Q to the 5th. all of these sequences have the same probability. All of the sequences with 2 h's and 5 t's have the same probability, p squared q to the 5. Okay. Now, how can we construct, okay, multiplication rule? Constructing such a sequence can be done in 2 steps. The first step is to select 2 slots out of the 7 for the h's. How many ways are there of doing that? 7, choose 2. Right? Well, there are 7, choose 2. Times the number of ways of selecting, well, the 5 slots for the 5 t's are sort of fixed. Once you've done that, you don't have to do anything else. There's only one way of putting the t's in, right? So it's the number of sequences which meets that requirement is 7, choose 2. Each one of them has the same probability of happening, p squared q to the 5. So what's the probability of flipping a coin, a fair coin in this case, 5 times and getting 2 h's and 5 t's? That probability is what? 7, choose 2 times the probability of each one of those sequences. This many sequences times the common probability of all of those sequences. So 7, choose 2, p squared, q to the 5. 2 data points and we're starting to see a pattern. This may be a bit optimistic, but yeah. Okay. So now let's generalize. We're going to roll 7 times. We're going to flip a coin 7 times. Probability of an h is p. Probability of a t is q is equal to 1 minus p. Okay? What's the probability of getting k h's and 7 minus k t's? Okay, let's look at a particular sequence and look at its probability. So there's going to be k h's, and then there's going to be 7 minus k t's for a total of 7 flips. Okay, so what's the probability of getting exactly that same sequence, keeping in mind that coin flips are results of the coin flip are independent? Right? So the probability of this exact sequence is the probability of is p to the k times q to the 7 minus k. Right? Because the coin flips are independent. The coin doesn't remember what happened before. Right? So the probability here is p times p times p times p, k times t times t times t, and so on. 7 minus k times. So this is the probability of exactly that sequence. Now, if we move these h's and t's around and we get a different sequence, the probability comes out exactly the same. All right? So the rearrangements of all of these sequences gives me each one of those sequences has the same probability. Okay, how many such sequences are there? 7 choose k, right? There are 7 choose k ways of selecting where the h's are going to go, and then you're left with the rest for the t's. So the probability is 7 choose k. P to the k, q to the 7 minus k. Okay? All right. We made this argument already. This is the answer that we get. What should my next step be? What should I do next? I started with 2 flips. I had 7 flips. Then I said, well, 2 h's, well, k h's. I've been generalizing as I've gone along. What's the next generalization?
N number of flips.
Yeah, we should have n number of flips. We're going to have a total of n flips. So we're going to say, what about k h's and n minus kt's? All right, so we're going to have k h's in a row. Let's say there's a sequence that has k h's in a row and then n minus kt's in a row, one after the other. What's the probability of that sequence? Well, p times p times c times p k times q times q times q times q n minus k times. So p to the k, q to the n minus k. Okay, how many such sequences are there? Well, there were n slots in the sequence. I have to choose k of them for the h's, and then there's only one way to put in the t's. So that's what? How many ways? N choose k. Okay. N choose k such sequences, all with the same probability. So the probability of k h's out of n tosses distributed anywhere, in any way, is n choose k, p to the k, q to the n minus k. Okay. And this works. We've used p and q. P is the probability of an h, q is the probability of a t. So it works for an unfair coin also. Right? All right, so now we're going to generalize again. We're no longer flipping coins. We are doing something. We're going to have n trials instead of n, we'll call them n trials instead of n flips. Okay? There are 2 possibilities. So you have n trials, you have 2 possibilities. It's traditional to call one of the possibilities a success and the other possibility of a failure. But we could call them red and blue, it doesn't matter. Just there are 2 possibilities. So you get a sequence of successes and failures. Okay? And each trial is independent. That's important. And the probabilities P and Q are not changing from trial to trial. All right? So, what's the probability of getting, you have n trials, the result of an S is P, the result of an F is Q equals 1 minus P. So what's the probability of getting exactly k successes in n trials? Yeah, it's the same. All of the same arguments hold. It's n choose k, p to the k, q to the n minus k. Okay. So now we've gotten a quite general result. So we speak of Bernoulli processes and the binomial distribution. Okay. So Bernoulli, what we've been talking about, the coin flipping, was an example of a Bernoulli process. So you repeat the same thing n times. There are two possible outcomes, traditionally called success or failure. The probability of a success we call P. The probability of failure, Q equals 1 minus P. Okay? And these P's and Q's remain constant from trial to trial, and the trials are independent. Okay? So if we do that, then, well, this is what we have been doing. Okay? When you flip a coin, the result of the first flip and the result of the third flip are independent. Right? So, an example. We toss a coin 3 times and see how many times we get an H. Right? So, probability of 0 is n choose 0, p to the 0, q to the n minus 0. Probability of a 3, n choose 3, p to the 3, q to the n minus 3. Okay? So, if you're keeping track of the number of successes, right, the random variable we're interested in, right, we were interested in the number of H's, for example. The random number, that random variable we call X, that's the one that we're interested in. Okay? Number of successes in n Bernoulli trials. And so we speak of we speak of a Bernoulli random variable, and it has a binomial distribution, which is the one that we've worked out. Okay? And so the probability that the number of successes is k, and given that the number of trials will be n, and given that the probability of a success, any one success in a trial is p, is n choose k, p to the k, q to the n minus k, and k can take values of 0 successes, 1 success, 2 successes, up to n successes. And of course, for any other value of k, this PMF should be equal to 0. Okay? Okay, so this, okay, I think I just called it the Bernoulli random variable. The binomial random variable, sorry, that's what I meant. Bernoulli trials, binomial random variable, okay? Okay, so if X is the binomial random variable, it has parameters n and p. So the number of trials, you need to know the number of trials. You need to know the probability of a success. K goes from 0 to n, and we're interested in the probability that x is equal to k, right? That's what the PMF is for this x. Okay? And if you were to graph this, you would see that it rises and then it decreases, and the largest value is when k is the number which is less than or equal to n plus 1 over times p. All right, so let's do an example. Okay, a doctor performs a surgical procedure. It has a success rate of 30%. What's the possibility that there will be exactly one success out of the next 10 surgeries? Okay, so look, we assume that the results of surgeries are independent. There's two possibilities, a success or a failure. And the success rate is 30%, so you're assuming that the probability of a success is not changing from surgery to surgery, and it's 30%. So that sounds like we can use our binomial random variable. Okay? So what is the possibility of exactly one success out of 10 surgeries? Right? 10 choose 1, 0.3 to the 1, 0.7 to the 9. Oh, yeah. Okay. So n choose k, p to the k, q to the n minus k. Okay? Okay. How would you find the probability of more than 7 successes in the next 10 surgeries? Yeah, so you could either add up the probability of exactly 7 plus the probability of exactly 8 plus the probability of exactly 9 plus the probability of exactly 10. Or you could take 1 minus the probability of exactly 0, exactly 2, and so on. Okay? What's the probability of 0 successes? 10 choose 0, p to the 0, q to the 10, right? Okay. Try this one. There are 5 questions, multiple choice test. There are 3 answers, 3 choices given. What's the probability of getting 4 out of 5 or 5 out of 5 correct answers just by guessing? Okay. All right, so what's the probability of this? 1, 2, 3, 4 are correct, and 1 is wrong. What's the probability of that? Okay. Well, the probability of this being, the first one being a success is 1/3. And then 1, 2, 3, 4. And then the probability of the last one being wrong is 2/3. They're independent, so I can multiply the probabilities of the individual ones. And then the number of such things where I don't specify which 4 are correct is how many ways? 5 choose 4, or 5 choose 1, same thing. So 5 choose 4. Okay, so that's the number of ways of getting 4 correct. What's the number of ways of getting 5 correct? Well, 5 choose 5, which is 1, times 5 correct with a probability of 1/3 and independent, times 2/3 to the 0, which is 1. Add up the probability of exactly 4 plus the probability of exactly 5, you get 11 over 243.
We could also have done 1 minus probability of getting.
Right, we could have done 1 minus the probability of exactly 0 minus the probability of exactly 1, and so on. Yeah. Yeah, well, okay, so finding the probability of a complement should give you the same thing, right? Okay, let's try this problem. A company knows that the widgets it produces will be defective with probability of 1%, independently of each other. The company offers widgets in packages of 10, and you get a money back guarantee that at most one of the 10 is defective. Yeah.
Is the probability of the complement going, is it going to apply like that? Because when we were discussing this seven or more example, we said that we just do more than 7 examples. We did 1 minus probability of 7, but the probability of 7 is
Now, okay, if we're doing a probability of more than 7 successes, then we would say probability of 8 plus probability of 9 up to the maximum number, right? Or we could do more than 7. We could say 1 minus the probability of 0, minus the probability of 1, minus the probability of 2, and so on and so forth. You can buy packages of 10 widgets. If you find, we guarantee that at most one is defective. If you find more than one widget defective, we'll give you your money back. The probability of any one widget being defective is 1%. What proportion of packages sold must the company replace? Yeah, so if you have, we're saying that if you have one defective, we don't if you have 0 or 1 defective, we don't give you your money back. If you have more than 1 defective, then we give you the money back. Okay? So X is the number of defective. X is the number of defective in a package. Okay? So I suppose you could test one widget after, we assume we're not destroying the widgets, so people will test one widget after another. Okay? So what we're being asked for is, what is the probability that X is greater than 1? Okay? So that's, okay? We can do that as 1 minus the probability that X is 0 minus the probability that X is equal to 1. Okay? Is that all right? Okay, so that's equal to 1 minus, there are 10 widgets in the package, right? So what's the probability that exactly the first widget is defective? 0.1. Sorry, 0.01. The probability then, the probability of, okay, no, okay, what's the probability that no widgets are defective? The first one isn't defective, the second one isn't defective, up to the 10th one is not defective. Right. So out of, so you have 0.99 to the 10, and you can write that as, we can write, that's harmless, right? 10 choose 0 is 1, and 0.01 to the 0. Right, just so it's in the form that we've been considering. Okay, minus the probability of getting exactly 1 defective. Well, the probability of getting 1 defective and 9 non-defective, let's say the first one is not defective. Well, let's say the first one is defective, and then the remainder are not. Okay? Now we could have the second one being defective and the other 9 are not, or the fifth one is defective, the other 9 are not. How many do we have where one is defective and the other 9 are not? Well, you have 10 widgets, you have to pick which one of them should be the defective one. So out of 10, choose one. The probability of that arrangement is exactly the same. So I think that's how it comes out. Is that okay? Okay, and if I'm saying the answer should be approximately 0.04. So you should try that. Okay. We want to know, as I said, we want to know the expectation, and we want to know the variance of any random variable that we look at. Okay, so I'm running out of time here. So, okay. Basically, I followed the proof that's in Proof Wiki. Okay. So, okay. So the expectation of any x is the summation over all the allowed values of x times the PMF. So that's from the definition. Now, what's the PMF? So the allowed values were k equals 0, 1, 0 successes, 1 success, 2 successes, up to n successes. So 0 to n, k. Now, what's the PMF for k successes? It's n choose k, p to the k, q to the n minus k. Okay. And then you go on for a bit. And you end with n times p. So if you have n trials and the probability of a success is p, right? So if you had, say, 10 trials and the probability of a success is 0.3, then you expect to have 3 successes. So that's kind of intuitive, right? If I flip a coin 100 times, what's the expected number of H's? 50, right? This is this n times p here. Okay? Except we're allowing the coin to be unfair also, right? N times p. Okay? And then the variance, once again, you can look at all the steps in Proof Wiki. I followed basically the steps in Proof Wiki. It also goes on for a bit. You get the variance is n times p times q. Okay? So the expectation for the binomial random variable is n times p, the number of trials times the probability of a success. The variance is npq, the number of trials times the probability of a success times the probability of a failure, which is 1 minus p. Okay? So if we go back to the surgery example, we said there was a 30% chance for success, 10 surgeries, then so if you've got a 30% chance of success and you have 10 surgeries, you expect 30% of those to be successful, so 3 successful. The variance gives n times p times q is 2.1, which is the same as 1.45 for the standard deviation, right? So if you were to get 4 or 5 successful surgeries or only 1 successful surgery, you still would not be surprised by that, right? You'd still be within 2 standard deviations of the expectation, which is, yeah. Okay, so see you on Thursday.